Hey guys, welcome back to the wonderful world of studying evolution. All right. Uh, I keep reminding you of this. I'm going to continue to remind you of this. What is evolution? Evolution is not an animal changing into another animal. All right. People keep telling me this. It's not. All right. Evolution is when the entire population changes. Right? Not one, but the entire group. And it's not just like a magic, like, oh, we suddenly became something else. No, it's about reproduction. Right? Evolution, animals will not change, but their kids might be slightly, the group of children might be slightly different than the group of adults, right? Because of genes. Think back to the previous chapter. Remember the previous chapter with the pedigrees and all that stuff that you hated? I know you hated it. You guys complained so much about it. It's important stuff, right? Everyone had two alleles, usually a dominant and a recessive, right? Sometimes two dominants, sometimes two recessives, but whatever. You have dominants and you have recessives. Imagine if the group of adults were spread pretty evenly, right? Like 50% of the time you came across dominant alleles, 50% of the time you came across recessive alleles. But the kids, what if the dominant allele was more reproductively successful, right? You know what that means? Then the ones with parents with dominant genes had a lot more kids. All right. That means the kids, you are going to come across dominant more than recessive. That's a change in the population at the genetic level. More kids have the dominant than the recessive. And then as those kids grow up and become the adults, again, dominant would be more reproductively successful. The ones with dominant genes are better with the ladies, passing on the genes more. And then the next group of kids in the whole population, you come across the dominant even more often and the recessive even less often. Eventually, that recessive may just outright disappear or just stay really low numbers. Right? It went from being even to you're never going to find that recessive again, probably. All right. That is a change across multiple generations at the genetic level of an entire population. That's what evolution is. And that's what we're going to be studying today. And guys, I'm going to apologize. I apologize so much on this one. I'm asking you to do math. Yes, I know, I know, I know. I can hear you crying in the distance. Oh, it hurts. Breaks my heart. Yes, we are mathing today. And it is going to be probably the hardest math I ever ask you to do. I'm not joking. I'm sorry. Yeah. But it's the hardest math I'm ever going to ask you to do, not the hardest math you've ever done. You do much harder math in math class. Right? So, what is this math? It is called the Hardy-Weinberg principle, or Hardy-Weinberg equilibrium, named after these two doctors, two scientists, Hardy and Weinberg, who were studying evolution, studying natural selection in evolution. Right? So let's take a look at a description of this, and then we will go to my whiteboard. All right, Hardy-Weinberg equilibrium, also referred to as the Hardy-Weinberg principle, is used to compare allele frequencies in a given population over a period of time. Allele frequencies, how often does a certain allele show up in percentages? 50% of the time, 20% of the time, 10% of the time? A population of alleles must meet 5 rules in order to be considered in equilibrium. Which, by the way, guys, equilibrium never really happens. All right, this is a hypothetical thing. Too many variables in reality. But 5 rules. 1, no gene mutations may occur and therefore allele changes do not occur. All right, we will consider a mutation a variable, and we're not putting variables in this equation. 2, there must be no migration of individuals either into or out of a population. Meaning, if somebody moves in, it's going to mess up our numbers. If somebody moves out, it's going to mess up our numbers. So that's a variable. No more variables. Random mating must occur, meaning individuals mate by chance. All right, it's not. There's no selective breeding. All right, no arranged marriages, and nothing like that. You know, two individuals happen to fall for each other. That's what we're going for. No genetic drift, a chance change in allele frequency. I mean, like a rock slide came and killed half the population. No, variable again. And no natural selection change due to environment may occur. All right, meaning Hardy-Weinberg does not care about the environment right now, right? It's about who can reproduce. It's not who can survive long enough in this environment. It's who can get the ladies, or who can get the guys. Right? That's Hardy-Weinberg. It's all about sex. All right, biology class, guys. We got to be able to say that without getting all immature about it. Hardy-Weinberg is all about sex. So there are actually two equations we need to know. P plus Q equals 1 and P squared plus 2PQ plus Q squared equals 1. Let's go to my whiteboard. Here. Need a platform to put my laptop on. Forward. All right, there is my whiteboard. Now we got two equations on this board. P plus Q equals 100%, and 2 squared plus 2PQ plus Q squared equals 100%. This makes no sense to you right now. Don't feel bad, right? Don't freak out. Don't be like, oh, it's too hard. I don't expect you to understand this yet. We're gonna get there, right? We have two equations because we're gonna have 2 points of view. And yeah, it's that hard. 2 equations for 1 problem. And this side is all about the alleles, right? The dominant alleles, the recessive alleles. So P is going to show the frequency of dominant alleles. So how often are you going to come across a dominant allele? 10% of the time, 20% of the time, 50% of the time. So F means frequency. I don't have enough room to write, so I'm just writing F. Frequency of dominant alleles. Q represents the frequency of recessive alleles. How often do you come across, in percentages, how often do you come across a recessive allele? And if you add them up, you should always get 100%. All right, so maybe if 20% of the time you came across a dominant, then 80% of the time you come across a recessive. And then you'll get 100%. You know, if it was 30% of the time it's a dominant, and then 70% of the time it's a recessive, you get 100% of all the alleles. Unfortunately, it's not that easy because we can't look at somebody and automatically know all of their alleles, right? Some people are homozygous dominant, some people are heterozygous, and that's going to mess us up. Another problem, we don't math percentages, right? We don't do equations with percentages. We got to turn this into a decimal. How do we turn it into a decimal again? Move the decimal point over twice. Right, so that means this is just 1. P plus Q equals 1. Same thing over here. We don't equal out to 100%. We're going to turn it into a decimal. And it's just going to equal 1. All right? That's the easy part. Cool. Same thing. So instead of 20%, it was 0.2. Instead of 80%, it was 0.8. 0.2 plus 0.8 equals 1. Math, right? 0.2 plus 0.8 equals 1, right? Simple math. Get a calculator. I will not stop you from using the calculator. I'm not that guy. But like I said, there's a problem with this really easy thing. I can't look at you and tell if you're homozygous or heterozygous, right? People, animals, all living things, they don't have just one allele. They have 2 alleles, one from mom, one from dad. Are you homozygous dominant? Are you heterozygous? Are you homozygous recessive? I don't know. But I do know for recessive, right? Reason why I had you do the pedigrees. You learned you can look at a person and tell if they're homozygous recessive. We're going to use that. So this equation over here, P squared. Remember, P represents dominance. So P squared means you have 2 dominant alleles, homozygous dominant. So this means this is how many individuals, percentage-wise, right, are homozygous dominant. And then P is dominant, Q is recessive. So this is going to represent heterozygous. And Q is recessive, so Q squared, 2 recessives, homozygous recessive. You add all of them up, and that's going to equal out to 100%, or decimal 1. Right? So let's take a look really quick at our setup that we're going to be using for this math. All right. So example 1, a population of cats can be either black or white. The black allele, capital B, so that's going to be our dominant, right, has complete dominance over white. So black is dominant, white is recessive. Given a population of 1,000 cats, 840 are black and 160 are white. Determine the allele frequency of alleles per genotype, and number of individuals per genotype. So to solve this problem, solve all of the preceding variables, and fill in all of these letters. That's actually going to be much easier than you think it is, guys. Don't freak out. Right? We know black is dominant, white is recessive. If white is recessive, then we know who is homozygous recessive. We know 160 white cats are homozygous recessive. It's the only way white shows up. Remember that? So how do we find the frequency of that, though? That's what Q squared means. Remember, Q squared, we're looking for frequency of individuals who are homozygous recessive. 160 of them are white, are homozygous recessive. That's not a frequency. That's a raw number. How many of them? I want that percent, or decimal, I want that decimal. How do we do that? How do you find a percent of something? Divide by the total number. All right? So 160 white cats, and there are 1,000 cats altogether. So 160 divided by 1,000. And actually, they do it for us right here. 160 divided by 1,000 is 0.16. All right, so we now know this is 0.16. It's going to equal 1. So plus something equals 1. Now that, but we can't figure these two out, right? We can't look at one of the black cats and know if they're homozygous dominant or heterozygous. That's an issue. That's where we have this one. Yes, you got to jump back and forth. That's the hard part. Guys, tell you a little secret here. I'm bad at math. I'm very bad at math. I actually was dropped down 2 tracks in high school, bad at math, okay? If I can figure this out, I believe in you. I know you can, all right? It's not as hard as you think. If you know Q squared, you can find Q. Just find the square root. That's it. Back to screen share. So find Q by finding the square root. The square root of Q squared. Q squared was 0.16, says it right here. Q squared, 0.16. So the square root of 0.16 is 0.4. So now we know Q. The square root of Q squared is Q. So the square root of 0.16, 4. P plus 4 equals 1. Was it 0.4? I think it was 0.4. I don't have my calculator right now. Let me double check that. Yes, 0.4. My bad. Yes. So 0.4. So what plus 0.4 equals 1? Well, subtract both sides by 0.4. So 1 minus 0.4. I can do that in my head. You can't here. I'll do it for you. Or decimal. That's a decimal point. It's not 10. That's still a 1. 0.4. That looks like 10 minus 4. So 6. Drop the decimal point down. 0.6. All right, so 0.6 plus 0.4 equals 1. we now know P is 0.6. They do a simple math right here. And I'm being long-winded, and that makes it seem hard. This is very easy math. If we know P, we know P squared. Just put 0.6 squared. Screen share. So 0.6. All right, so find P squared. P squared is 0.6 squared. That's 0.36. So over here, 0.36. If P is 0.6, P squared is 0.6 squared. 0.6 squared is 0.36. Again, use a calculator. Don't overthink this, guys. All right, now, here's the hard part. This is actually the part I consider the hard part. I don't know why. It just extra steps. Tedious, not hard. 2 plus P plus Q. I'm sorry, times. 2 times P times Q. We know P and we know Q. This is not squared. Right? It's regular P and regular Q. So it's going to be 2 times 0.6 times 0.4. So 2 times 0.6 times 0.4. Get your calculator out, do that math, and you get 0.48. So rewrite it down here. 0.36 plus 0.48 plus, that's not a plus, that's a decimal, plus 0.16 equals 1. And go ahead, add them all up. It equals 1. This plus this equals 1. That's a big one. Which means, we turn those in percentages, right? 36% of the time, you would get homozygous dominant. 48% of the time, you get a heterozygous animal. Those are 2 different black cats. Right? And then 16% of the time, you get homozygous recessive. Okay? And those would be all of the answers. Remember, frequencies can be checked by substituting the values above back into Hardy-Weinberg equation. You can just plug them in, add them up, it should equal 1. All right? So we are going to have some work to do with this equation. I'm going to give you some setups. You are going to find out what is missing. And you'll have some information. You should be able to find out what is homozygous recessive. And from there, work it all out. All right? Please, oops, here. Please, guys, come to my office hours. Monday, Wednesday, and Friday, 9:30 to 12:30. I have Zoom, just like this is right here. I have a whiteboard. I will walk you through it, all right? I will help you do this. Come to my office hours. We will go through this, right? I'm up very early and ready to go. At the time of recording this, it is 8:44 in the morning. So by 9:30, believe me, I am ready for you. Come see me anytime in my office hours. I will not be too busy for you. This stuff is confusing. It's confusing when I'm there to help you. So you can, like I said, I believe in you. I know you can do this. I still want to help. Please. All right? Good luck, guys.